Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about variable specific impulse, magnetoplasma, rocket or VASIMR. So let's dive deep into it. So what exactly is the problem? Well, problem is that the moment you start to calculate the distance between celestial puppies, things get far, like very far. For example, most humans have some idea of moon because we can see it. That puppy is barely 1.28 second away. Let's just say maximum 1.8 second away. So it's not that far away, practically speaking, in celestial sphere. Let's just compare that to Mars, our next love interest. Mars at very good day, like you are things are working out for you, things are very well aligned, stars literally aligned. At that point in time, it's gonna take 193 seconds at light speed. That's far. And again, if things are not aligned, basically you have Earth, Sun and Mars, that point it's going to take you 22 light minutes, full speed, 22 minutes, not seconds, minutes. And let's go to Pluto. Pluto is like 4 hours 45 minutes, or in seconds, 17,100 seconds. That's far, ludicrously far. So fundamentally, what does this mean? This simply means chemical systems only have enough thrust. It does have thrust. That's the good part of chemical system. It has more oomph. It has more than enough, but the moment you want to push it above moon, basically anything further than moon, it's too goddamn slow for that. For getting off Earth, awesome. The moment you want to have any dream other than moon, it's like, bro, no. So how do we right now go? Well, we can send very small thing. That's why even the best thing we have sent to Mars, it's basically a Tata Nano car. It's a barely 1 ton vehicle. Like, and again, this is the scoop we got. Like, that's all we got on Mars. Like, we have JVC, it's like, we're gonna drill up to 2 meters. And JVC is like, hello, take it and go, 2 meter, go. And nobody got time for it. We can't send it. Like, we want to make it, we love to make it, it's just we can't send it. Chemical rockets just does not have the oomph required to do that thing. So the moment you want to expand beyond moon, so at that point in time, it's just things become very small and you have to just wait and pray that nothing goes bad happen. For example, we launched a system in 2006. Let that sink in. In January 19, 2006, we yeeted a craft, and that craft was so slow that we have to double charge it from Jupiter. That happened in 2007. And then slowly, over time, we finally reached basically in 2015, we reached basically Pluto. Basically, imagine what computers were in 2015 and now imagine what computers were in 2006. That was the hardware gap we had to deal with, simply because it takes too goddamn long. So, and again, Voyager, that thing took its sweet time. So realistically speaking, right now we can only send small things and we have to wait and pray that nothing bad happens. It's like, this is not a tangible way of doing it, and it's on physics level. It cannot be bypassed no matter how much Elon Musk you smoke. Chemical rockets just does not have the oomph required to do it. So what are the primary hurdles? Well, primary hurdle is erosion. Well, because you have to understand, if you want high velocity to really go like millions of kilometers, billions of kilometers, you need velocity. Thankfully, there is no drag in space, or serious enough drag. You can get to that speed. That's the cool part. Problem is that if you compare the exhaust velocity, that will affect your final speed before you run out of propellant. You can go higher than your exhaust velocity, but not by too much. And ideally, you want ludicrously high exhaust velocity. So solid rocket will give you around 2.5 kilometer per second, plus and minus here and there. So this puppy have the oomph. Like, this is why this is used for ICBMs, missiles. These puppies are like yeet, but they do not have the mileage. So basically, they are a sprinter, not a marathon runner. But what if you want best of both worlds? You want like more oomph, but you want it to run like, marathon. At that point in time, you use liquid systems. Liquid system can easily go up to like, let's say, ideal scenario, burning liquid hydrogen and liquid oxygen. That puppy can give you around 4.8 kilometer per second. That's why generally hydrogen is preferred for upper stage. And then if you are burning methane and liquid oxygen, you are looking at around 3.8. So you can see these velocities are just not good enough for, well, Mars. It's just not good enough. Now let's compare that to ion engine, the next alternative we have, this puppy. This puppy's exhaust velocity is 42 kilometer per second. It's fast, ludicrously fast. Meaning, if you fire this puppy and let it fire for 5 years, the top speed that this puppy will reach would be unimaginable by any other system. Flat out, we do not have anything that can come even close to this sort of speed, because again, exhaust velocity is so goddamn high. Then why don't we use it for everything? Yeah, we do, but it has a limitation known as pushing a train using a mouse. NASA scientist. So this is NASA next thrusters testing. Yeah, that puppy only creates 24 grams of thrust. Tons of thrust, hundreds of tons of thrust, grams. So yeah, that's the issue. Like you can see here, like this puppy, Saturn V, this puppy used kerosene, like raw, oomph. And you can see it has like cool gas, like such a cool gas of around 600 degrees, 700 degrees Celsius. And then it has the fire. The cool gas was from pre-burner. So to make sure the nozzle did not melt. So again, iron engines does have the velocity, it just does not have the oomph required to do anything. It's like it's very good. Like once you throw something in, let's say Earth's escape trajectory, then you can go YOLO. And then it's like this is the way of doing it, and we have been doing it. It's just that it takes many years. Like in this scenario, NASA's next scenario, they ran it for 5 years, 5.5 years continuously. I think the hours was like 48,000 hours or something like that. Like then only it got that kind of speed. It burned through very little amount of propellant, less than 1 ton of propellant was burnt. But again, it got speed, like yo kind of speed. So iron engine works for years, but again, there lies the problem. You still are waiting because again, low thrust. But again, final velocity would be high. So that's the good part. And because you are talking about iron, it does not matter whether you're making iron of something corrosive or not. Iron engines is like inherently dealing with ions. Ions itself is inherently corrosive to engine parts, meaning no matter which design you have, whether you have grid design or you have a gridless design, basically you do not have the neutralizing grid, you have a Hall effect, like a electron gun on the side. Yeah, both of them will inherently destroy itself over time, not on day one, but like 6-7 years continuously. Yeah, it's gonna self-destruct because the material's lifespan is limited. Now that itself is not an issue. If it can last for 30 years, more than good enough. But problem is you can't increase the power. So it's like, okay, if this gave us this kind of power, why not just increase it? Yeah, you can't. Like physics wise, there is a limitation, because if you keep increasing the energy, the ion will become far more violent, far more difficult to handle. And the thruster designs that we have right now, they are not designed to go really balls to the wall, so to say. So we can't really, okay, what if we put 200 kilowatt? They're like, yeah, put way too many small engines, and penalty of that would be power to weight ratio will go down. So we are not only limited in lifespan. So even if it's like, oh, this is good enough, let's just say we use RTG and just have some amount of power going into it, continuously running for 40 years like Voyager, yeah, this will not last. So lifespan is limited, and then you have power limitation. So you can't just go YOLO on it. So that's the limitation of erosion, because even if you have an electron gun and if I keep bombarding electrons from it, electrons have mass. Over time, this will just evaporate away. So fundamentally, and again, not to mention everything that is getting bombarded and destroyed, yeah, that's not comfortable. So erosion is a fundamental limit why we can't just go YOLO on iron engines and make them the Star Wars iron engine. So we come into VASIMR. Now this is an electrothermal thruster. Basically you're taking something and boiling that up, and you're like, wait, that sounds literally like a nuclear thermal rocket. Yes, it's just much more faster. So electrothermal, and how the heck this can have more power and more oomph? Well, simply because it does not let exhaust touch anything. It's violent, it's corrosive, it's destructive, but it's not touching anything. It's literally like how we have basically fusion reactor, which could have like 25 million degrees Celsius. Then why the heck wall is not melting? Yeah, it's not touching it. No touchy. No touchy rule is applied. So you do not let naughty things touch things. That's the rule number one. And that's why this engine can have amount of power. So this system is easily scalable up to basically megawatts. Basically this design was tested for 200 kilowatt. You do not have a single iron engine that is like 200 kilowatt. They have tested 200 kilowatt, and they can keep scaling it up. There is nothing physically limiting it for, like, until you start to go into gigawatts, then it's like, yeah, then you might have to like tone it down, but generally there is no physical limitation on it. So that's the good part. And what kind of escape velocity? Because that puppy went up to 42. What kind of escape velocity we are talking about this puppy? Yeah, 50 kilometers per second. And be mindful, that's the starting point. You can go much higher than that. Like, it's just limited by power. The more power you add, the more basically kilometer per second you can achieve based on your design goals, so to say. So it is bonkersly powerful and has enough velocity that you can actually go to Pluto quickly. And on top of that, so far it's just a better engine, but on top of that, why it has a VA in its term is the fact that it can control a specific impulse. Now, why is that? Well, all things are power limited. It does not matter whether you have solar engine, does not matter whether you have nuclear engine. You always have limitation of power. You will have a power envelope for your propulsion system. Let's say 200 kilowatt. That means you have 200 kilowatt. How you utilize it, it's up to you. So if you are like, let's just say you launch this puppy from low Earth orbit, things are docked, things are good, but now you need the oomph, because if you do a very, very low thrust push off, it could take like freaking 6 months going from low Earth orbit to geostationary orbit. That may not be desirable. But here you can reduce the specific impulse, meaning you reduce the specific impulse, increase the flow rate. Basically, rocket equation is very simple: how much you throw and how fast you throw. So you reduce how fast you throw, but you increase how much you throw, and it gives you high thrust, meaning you can go from, let's just say, low Earth orbit to geostationary maybe as quickly as in 1 week, rather than waiting for 6 months. You're like, hey, 1 week, we good, we got this. So you have that thrust vector control, where it's like how much oomph we are getting out of it. And once you're outside, let's say you went from low Earth orbit to escape velocity, you did it with maximum thrust. Now what? You change the engine gear. Basically, you go from lower gear to higher gear. Now you have high specific impulse, meaning the flow rate will go down, meaning you will be far more fuel economical, meaning the final delta V would be much higher. So not only because you have the thrust vector control, it allows it to handle gravitational in and out, gravitational dipping. So that's the benefit of it. And can't you do that with ion engines? No, the specific impulse is fixed based on the design and the voltage used. Here you can actually throttle it. So that's the whole point. This is why it's such an attractive thing, and US government has been burning money on this for almost 20 years, or maybe more than that. So that's why everybody is excited about this. So what is the design principle of it? Well, very simple. You start with hydrogen, because obviously if you have a temperature, the highest velocity of mass you can get out of it has to be light. Hydrogen is the lightest, go YOLO on it. So great exhaust velocity requires hydrogen, you use hydrogen. Now you ionize this puppy with helicon antenna. Now if you look into this design, you have gas gets into plasma. Now this plasma is hot, it's almost like a 200 K degrees Celsius, but again, because it's relatively cooler, yes, relatively cooler, so they are calling it cold plasma, but it's not cold. You have plasma and you are dumping a lot of kilowatts here. So this helical antenna, utilizing 13.56 megahertz, it's coupling all its radio frequency energy into the gas flow, and gas is becoming ionized. Now after that much ionization, here's the key part. Ion particles are basically controlled by magnetic field, meaning you can make sure the no touch rule applies here. You have a giant electromagnet, which is basically a superconducting magnet of few Tesla, and few Tesla, you do not need like bonkersly high, just 1 Tesla will also do, and that impinges it, meaning it can no longer touch anything. So you can increase the temperature as much as you want, and that superconducting coil is also acting as a nozzle design for you, because again, you must have seen nozzles have what we call converging and diverging for maximum efficiency. The superconducting coil, magneto dimensions here, is acting as that. So basically it's impinging it, and that's why you will see this impinging wherever you have superconductor there. So superconducting is allowing you to have control over the situation, and acting as a nozzle is pulling double duty. An ion cyclotron resonance heating stage, basically the final puppy. Now this final puppy, you have basically, you took a gas, you turned into a hot plasma, and then you confined it with a superconducting coil, and after that you really dumped heat into it, meaning this time you're going to dump heat at around 1 to 2 megahertz, almost like a microwave, but again we are talking about like multiple kilowatts. At that point in time, you're going to have ludicrously high temperature. What kind of temperature we are talking about? Million degrees Celsius. They started with 1 million degrees Celsius. Now they have reached 2 million degrees Celsius. And be mindful, that's not limited. It's just like, as long as you can keep improving the design of radio frequency and coupling efficiency and making sure all other things can handle it, you can keep increasing it to even 25 million degrees Celsius, as long as the magnetic field is strong enough to confine it. And benefit of that super high temperature equals ludicrously high exhaust velocity. That's why it's not limited to like, okay, it can maximize up to 50 kilometers per second. No. This can easily go to 100 also. But assuming you have very efficient and powerful reactor to do that. So this is the whole design of it. So basically you take your gas, you convert your gas into ion, magnetic field start to act on it because it's an ionized stage. After that you impinge it, because again that's the whole point of conductor, and then you reheat that puppy. You dump energy into it like there is no tomorrow, and then you just expand it. And again, that's the magnetic output of it. You expand it. This is the last coil where you reheat it, so to say, and this is the main hot part. This is the million, and then you expand it. So fundamentally, the efficiency is limited by 2 core elements. First element is how efficiently the energy from radio frequency is being coupled to the ions and gases. Again, that's why the frequencies are not fixed. It requires a feedback loop, to so to say. So it is perfectly coupled. That coupling, how much coupling you are getting, that will constrain your final output efficiency. Another is power conversion, because you are talking about hundreds of kilowatt of energy. Converting hundreds of kilowatt of energy electrical into radio frequency, it's not something that we normally do. Even mobile towers do not go that high. So that does require power electronics to be very efficient, so it can have final conversion efficiency high. Superconductor does not require too much other than some active maintenance, because again, you are talking about the sort of high temperature. I'm pretty sure it will have some amount of X-rays, some amount of this and that. It will go through it. It will over time, not on day one. Over time, it will start to boil away things. So it would be reasonable to have some sort of cryo coolers on the superconductor, so maintain it for years on end. But again, the core benefit is nothing is touching anything else. Once the gas comes out, the end, you are not touching it. Once it's converted into ion, it's perfectly trapped into the magnetic system. You do not get any other input to it. So it's not touching, it's not eroding anything away, and heat is limited by how much energy you have. If you have higher energy budget, go YOLO on it. But be very mindful, this design does work better at higher capacity, not at smaller one. Meaning if we have ion engines that were like, okay, we had 7 kilowatt ion engine running for 5 years, why not make a 7 kilowatt of this? It does not work that well. Basically, this system benefits the more kilowatts you have. So if you are starting with like 50 kilowatt, now this is your guy. If you're like 200 kilowatt, this is your guy. So more the power, the better these systems work and the more efficient it becomes. So it's not very what you call finicky and small thing. It requires like big oomph. So, but again, this works. Nothing is too complicated, and again, we have been building it for 20 years. We just have never flown it because we did not have power budget for it. So there are design is not that complex, finicky, not complex. So what are the hurdles we are talking about? Well, hurdles is just that it does not work at small scale, or somebody may figure out, like, let's say in future, a 10 kilowatt system that is like super efficient and truly utilizes its principal efficiency. That would be awesome, but I have not seen any design. And again, the company that is working on it, Ad Astra, they keep working on bigger and bigger one, because again, this is the only system that you can have in principle that can actually take a giant craft like this from basically low Earth orbit to Mars orbit there, come back without too much hassle, without requiring like 20 refuel for per starship. Yeah, that's stupid. This can actually do it. So fundamentally, maybe somebody can figure out that, but as of now, I have not seen it. And again, they are not interested, because again, the moment you compare it to kilowatts, it's like, hey, why spend so much money? We have an engine in home. And again, 40 kilometer per second exhaust is still fast enough. So that is there fundamentally. And again, it's not feasible without a fusion reactor. What about solar? While people have thought of it, it's just that solar panels are not that great, and not to mention the moment you start to go away, because again, it's Mercury, Venus, Earth, Mars. Mars is further away than Earth. Penalty is that solar panel loses its capacity. If we were like, if our interest was like, going from Earth to Venus, this will be solar only. We are not doing that. So it's without fusion reactor, it's not, and again, you can't even think about Pluto or gas giants without fusion reactor. So that is there, and it does require utilize multiple cutting edge technologies. So superconducting coil, well, again, is NASA has been testing superconducting coil in ISS. So we are working on it. The parts of the design is under construction, is in utilization. It's just that it's one thing to have some experiment versus, oh, we built it and we kept running it for 5 years. That's a different thing. So it's not ready for prime time, because again, other things are also not ready. So I'm pretty sure the company can just, if they get funding, they can just, yeah, here's the ready design, at least Mark 1. But they can't do it because fusion reactors are not ready enough, which is ironic. We used to have that. Like, we used to have nuclear fusion reactors in satellites, Soviet era, Cold War era. And again, they were not running on what you call basically piezoelectric, I'm saying thermoelectric system. They were utilizing something different, and some actually tried Stirling engine also. So we had the technology, we just like, we're too spicy right now. So that's it. But again, let that be very clear. This, at this point in time, is the only next generation technology with some genuine promise. Meaning, can we make this? Yes. Can this be really powerful? Of course. As long as you have the electrical budget, this puppy is like, even in few tons of propellant, we can just like yeet things faster than you can ever believe. And not to mention, because it has thrust control, you can go like, okay, I'm going super duper hyper fast when we are going to Pluto. And at the time, Pluto, you do a Bratislava burn and then increase thrust. And you can actually dock there, dock as in like get captured by its orbit, so to say. So you can actually study it, not just do a flyby. Can you imagine, we actually did that? We sent something and all we got of Pluto is like, done. We could not stop. We did not have enough fuel for that. So that's why this sort of system can work in mysterious way. Very awesome. It's like, hey, I'm dumping all the energy from a nuclear reactor or super efficient RTG, and all the energy is just going into propulsion. And once I'm there, I'm like, I'm gonna go very close to the surface, and then I'm gonna do, you know, back burn. So it is awesome, but it does have some hurdle, and this is truly next gen. Iron engines, we are sorted. This puppy is the next one after that. So this was my presentation on basically VASIMR engine. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.